All right, so good afternoon. So we're going to go over just a brief review of kind of everything, putting it all together, getting it in one spot so you can kind of look over your notes. I'll also be posting the practice test so you guys can actually look at the test and see that you know how to do everything. So let's take it all the way back to our very first lesson. When we started with just a relation. So some combination of things that are related to each other somehow. So we had something like maybe A, B, C, D, and then they were going to some outputs, 1, 2, 3, 4. So this could be some kind of relation. It would give us directed information as to which ones are related to which. And this was one of our examples. This was a mapping diagram. So when we looked at this information, when we first started looking at relations, we talked about a couple things. We said that the domain of any kind of relation is just all the inputs that are available for that relation. We said that the range was all the outputs. So in this case here, our domain would simply be all of the available inputs. So we'd have A, B, C, and D, and our range would be the available outputs, 1, 2, 3, and 4. Now, when we talked about relations, there were 4 ways that we said that we could actually show them. So the one I just gave you is a mapping diagram. But there are 3 other ways that we could also show them. We could show a relation using ordered pairs. And those would be an example of like when we have our XY coordinate points, these are ordered pairs showing the relationship between them. We could have a list of table values or a table with labeled values in it. So that would be an example where we could draw out and we might have something like age versus height. We could have 10, 11, 12, 13, 5'4", 5'6", 5'8", 5'10". You know, this would be another example of a mapping. So we have our table, and then our final one, the final of the 4 ways that we were supposed to show things, is via a graph, where we could simply have plotted points or something else showing what the relationship is. So again, when we first started talking about relations, there were 4 ways that we could actually show it. We could show it through a mapping diagram, we could show it through ordered pairs, we could show it with a table of values, or we'd show it with some kind of graph. So those were our 4 basic means of showing a relation. Now, inside of that relation, when we were talking about domain and range, there are a couple different ways that we could actually state a domain or a range. So our first and the hard one was actually to list out in set notation. So when we use set notation to describe a domain, to describe our inputs, we always did it a very particular way. We had a curly bracket saying that it was going to be the start of a set. We would list what variable it might have, and then we have the colon symbol for such that. Once we've listed that, we would then list any kind of rules that might apply to our set. So it could be something as simple as we could list out the information. So in that case, in like our previous example, it could be something like A, B, C, D, and then we close the curly bracket to show that we're done. But whatever it might be, we would have our rules in that middle portion. So an example from some of the homeworks might be something like the set of all x such that, and then maybe we'd have an interval, x is less than 5, or an inequality. This could be an example of set notation. It could be something that looked like the set of all x such that, and then we could say some kind of other rule, x is even. So whatever it might be, we always follow that same pattern for writing out our domain. We have the curly bracket, we have what variables being measured, such that, which is the 2 dots, and then whatever rule might apply. So this was our set notation. The second way that we were talking about domains is we were talking about inequality notation. So inequality notation is where we had those less than, greater than, less than or equal to, greater than or equal to notations. So we had things like less than, greater than, less than or equal to, greater than or equal to, and we used those in inequalities. And our key for working with those was also remembering that those corresponded in a specific pattern. So if we had no equalities, we were also going to be using parentheses. And we were also going to be using like open circles when we drew things. When we had an equality, those matched together with using brackets and closed circles. So there's a quick example for these. If we were drawing out something like x is greater than 5, when we drew that on a number line, we would list our 5. We know it's greater than or equal to, so we're going to be using a closed circle in this case. And then it's everything greater than that. So that's how we would draw it. If I wanted to use another way of showing it, then we'd have our third way, which was our interval notation. So interval notation was basically just describing it from left to right or bottom to top. So in our same example here of x is greater than 5, the furthest left we can go is 5, so we would have used a bracket. And then we go a comma, and then as far right as we can go, well, we're going on forever, and that was our infinity. So just real quick, these were our 3 basic ways of writing our domains or ranges, using set notation, inequality notation, or interval notation. Now, when we started to put that together, what we'd have is we'd actually have a graph or something similar, and we'd have to identify the domain or the range. So we'll get to that here in a little bit. So outside of talking about domain and range, we also discussed whether or not something was a function. So a function was a very specific type of a relation. In a function, each input could only have one output. And that was our big rule. So graphically, when we looked at these, we applied what we called the vertical line test. If we could draw a graph of some kind, and we looked at it, and we can draw vertical lines that it only touches at most once, then this was considered a function. So that worked. As opposed to, say, if we go back to a graph that looks something like this, here, if we draw a vertical line, it impacts more than once, so it was not a function. Mapping-wise, when we drew these out, that means that each starting point could only be going to one output. So as long as each input only went to one specific output, we were okay. But the second that that went to 2 different outputs, it was no longer valid. So if one went to both A and B, then this would no longer be a function, or one input has 2 different outputs. Now, as we went along, we then started talking about using these notations for bigger and bigger rules. So in our second section, we started graphing things. And this is honestly where people had the most trouble overall, is how do we graph again? What do graphs look like? So let's kind of put together our 4 parent graphs and talk about domain and range and all of that involving them. So we were responsible for 4 parent graphs for these lessons. So our first one was y equals x squared. If I had to plot points or to draw out y equals x squared nice and neat, it is our basic parabola graph. It starts right here at the origin and it forms our nice pretty U shape. Now, as we went to go talk about domain, range, and everything else, we'll kind of go over it in terms of these parent graphs. So our domain is going to be all of the x values that can be used. So as we look at these, the x values, we can go as far left as we want, and we can always find an x that we can put in. We can go as far right as we want. So we could always find an x we could put in. So our domain is a couple different ways to write it. In interval notation, we could go from negative infinity to infinity, all the way to the left as far as we want, all the way to the right as far as we want. We could have written that as the domain is the set of all x such that And then we could say something like x is an element of the real numbers, meaning it could be anything that we want. We could have written it out in set notation using intervals. We could said, or using inequalities, we could say x is the set of all x such that, and then here, what we would want to do is actually write x in between the infinities using the inequality symbols. So we have negative infinity is less than x is less than infinity. This would also work as a way to describe the domain. So when we write these out, there's a lot of different ways we can actually phrase our domain and range. So our range worked the same way, but now we're only looking at the y values. So as I look at my parent graph, I went from bottom to top, and the lowest value that we can start at is at 0. So we started at 0, and then we went up forever. So my range would be 0 to infinity. We can include 0, so I use the bracket. We can't include infinity, we never get there, so I use the parentheses. So that was my range. Again, I could draw it out in different ways. So as an inequality, well, that's including 0, but y gets bigger and bigger, so that's y is greater than or equal to 0. I could write out in set notation. So that's the set of all y such that, and our rule would be y is greater than or equal to 0. So I have my domain and my range for that parent function. Our intercepts are going to be wherever it touches the x or y axis. So in this case, my x-intercept is 0, 0, and so is my y-intercept is 0, 0. The final thing we talked about in regards to the way that graphs looked was asymptotes. And remember, an asymptote is going to be a line that a graph gets closer and closer to, but does not actually touch. So an example would be we end up with something coming up that never actually gets there, just kind of evens out. So that was one of our asymptotes. In this case, our basic parent graph of y equals x squared, we would have no asymptotes. All right, we were responsible for 4 different parent graphs. On the test, I could ask for any one of them and then ask what the domain, the range, intercepts are. And our 4 parent graphs were 1, y equals x squared, 2, y equals x cubed, 3, y equals 1 over x, and 4, y equals the square root of x. So we need to know what those 4 graphs look like. You don't necessarily need to know every single little point, but you should be able to look at it and then just sketch generally what it looks like. All right, so the next thing we kind of talked about, after we decided to look at key factors of graphs, was function operations. And this, some people had a lot of trouble with, in particular, one example. So I'm going to show an example of each of them. So we talked about ways of combining functions. So I'm going to choose a simple example. I'm going to show all the different ways that we can combine them. So let's start with a basic f of x equals 2x minus 1 and g of x equals 1/2 x plus 3. So there's a bunch of different ways that we can notate how to do these. And I think that was one thing that people got kind of confused on. So to add them, they could write it out as f plus g of x, which is probably the most common way. And remember, that just means we're going to take our f of x and we're going to directly add it to our g of x. So that's exactly what I'm going to do with the function notation. I'm going to replace the names, the f of x and the g of x, with the actual equations that they gave us. So f of x was 2x minus 1 plus, because that's what they're asking us to do, g of x, which is 1/2 x plus 3. Once I've substituted it in, always using parentheses, then I can go ahead and actually just simplify the expression down. So this is 2x minus 1 plus 1/2 x plus 3, which gives me 3/2 x plus 2. And that is definitely wrong. That is 5/2 x. So we get 5/2 x plus 2. If we did a minus instead, oftentimes shown with notation like this, that's just saying subtract the other one. So I'm going to do the exact same process. That's f of x minus g of x. and I can actually just plug them in, still using the parentheses to protect myself. So that's 2x minus 1 minus our g of x, which is 1/2 x plus 3. Now here, because -1 counts as a constant out front, we need to distribute. So that's 2x minus 1 minus 1/2 x minus 3. 2 minus 1/2, there's our 3/2 x. And then -1 minus 3 is minus 4. So there would be my f minus g of x. When we go to multiply, here's where the notation gets a little bit weirder. So there's a couple ways. Sometimes they'll just show a solid dot, which is fairly common. Sometimes they'll use an asterisk. Sometimes they'll just write them next to each other. All of these simply mean multiplying. So when we go to multiply these, we're going to take our entire f of x, and then we're going to multiply it by whatever our g of x is. And again, we still want to use parentheses. So our f of x is 2x minus 1, and our g of x is 1/2 x plus 3. Here we have two items, both of them are binomials, so we need to actually distribute. So 2x times 1/2 x is x squared. 2x times 3 is plus 6x minus 1/2 x minus 3. So this was that FOIL that we learned it back in Algebra 1. From here, I can combine any like terms. So that gives me x squared plus 6 minus 1/2 x. Honestly, if you're having trouble with the fractions and you want to write it out as a mixed number, I'm okay with that. We should try to keep it more in terms of improper fractions, but it's not that big a deal. So in this case, that's going to be 11/12 x minus 3. Or you could have just put 5.5 x. So there's my multiplication, and I've simplified it down. When we did division, that's usually going to be written with one of them over the other physically. And that's the pattern we're exactly going to follow. So we're going to put one on top of the other. So f over g tells me to put my f equation on top and my g equation on the bottom. Now, what I'm looking for at this point is that we simply set this up properly first and then find any problems with our domain. So remember, for all of these, domain is usually going to be all real numbers. They tend to work for no matter what we want to do. The only time we have a problem is any time that we have a variable in the denominator of an expression. Since we're not allowed to divide by 0, to find our domain, we need to see what is going to mess it up, what is going to involve us dividing by 0. So what I'm going to do is I'm going to take the denominator, and I'm actually going to set it equal to 0 and figure out when that gets messed up. So I can solve the 1/2 x plus 3 for 0, and I get x equals -6. So if x equals -6, our whole expression becomes something over 0, and we can't divide by 0. So my domain then is going to be all real numbers except that x cannot be -6. When you go to do the test, if you actually get stuck here and you can't simplify this down, say it's something bigger or uglier, then you can simply write out that that domain the whole bottom part cannot be equal to 0. And I'll accept that from you. Next part of our compositions was actually putting them together. So we'll start with a new f of x and g of x. So I'll do something a little bit simpler. F of x equals 3x plus 2. G of x equals 5x minus 3, whatever. So we had a special new notation this time called a composition where we used an open circle in the middle. And what that meant is that we were going to put the inner one inside of the other. So this is the same thing as f of, and then we're placing the g of x inside of it. So when I go to write this out, I'm actually going to take f of x, or my g of x, and put it right in there. So that's saying, well, let's do f of, and instead of g of x, we're going to do 5x minus 3. So I've directly substituted it. From here, our normal f of x equation, when it's just dealing with x, was 3x plus 2. But instead, we're saying anywhere that we see an x in our actual equation, we're going to replace it with this whole g equation. So f of 5x minus 3 then is our regular f equation, which is 3. And instead of x, I'm going to write this whole thing, 5x minus 3. So I've placed the entire g of x right here into the f of x equation where I saw x. Now I can simplify, I can distribute, so that gives me 15x minus 9 plus 2 is 15x minus 7. This would be f of g of x. Order matters for these. So if they gave us instead g of f of x, we would do the same process, but now we're saying that f is in the middle. So that's saying take our f of x and put it inside of the g of x. So my f of x equation is 3x plus 2, and I'm going to put that entirely inside the g equation. So now we're asking for g of 3x plus 2. My g of x is 5x minus 3, and I'm going to take this, and everywhere I see the x, I'm instead going to replace it with the 3x plus 2. So g of 3x plus 2 is 5, and instead of x, I write my f equation, minus 3. I can now simplify this, get 15x plus 10 minus 3, and I get 15x plus 7 is g of f of x. The final thing that we did with compositions is we said, what if there's a composition with an actual number? So again, I'm going to start with just a couple equations. So f of x equals 2x minus 1, g of x equals 3x plus 2, whatever they might end up being. And they could ask us for f of g of, and then instead of x, they could have an actual number, like 3. And I said there are two main ways you can do this, so I'm going to show them both. The first way is we just pretend that there is no number. So I'm going to do f of g of x first. So I do my f of g of x, so that's going to be my f equation is 2x minus 1, so that's 2. Instead of the x, I write the entire g equation, 3x plus 2 minus 1, and I simplify this. So that gives me 6x plus 4 minus 1 is 6x plus 3. Now that I've simplified that, now I can actually plug in the number that we're going to use. So that gives me 6 times 3 plus 3 is 18 plus 3 is 21. The second method we said is to work our way inside out. So here, when we're given the f of g of 3 is there, we actually can write that out as f of g of 3. So the first thing I'm going to do is actually solve for g of 3. So remember, when we actually evaluate a function, what we're doing is we're just plugging in that number for it. So when I put that in, that's 3 times, and instead of x, I'm actually putting in the 3 plus 2. So that gives me 9 plus 2 is 11. So g of 3 is 11. So now I'm going to bring this down again, and it's no longer asking for f of g of 3 because we know what g of 3 is. So now we're just looking for f of 11. So that's going back to my f of x equation, and I'm going to plug in 11 for it. So that's 2 times 11 minus 1, which gives us 21. You'll notice that they both worked out the same. Either method is perfectly acceptable. It's just whatever one you feel more comfortable doing. Okay, our final piece of our little whirlwind review here was inverses. So an inverse undoes what a function is. It actually kind of takes what the function did and it reverses it back to the original. So there are a couple main processes we really needed to get down. So our first was how to find an inverse. So to find an inverse, we had several distinct steps. So let's take f of x equals 1/2 x minus 4. So our steps to find an inverse is first, we rewrite the f of x, or we rewrite the name with y. So instead of f of x, I'm just going to write y instead. So now it becomes y equals 1/2 x minus 4. Our second step was to switch the x and the y. When we switch them, we're actually just going to physically move them to either side. So x equals 1/2 y minus 4. Our third step is to now solve for y. So remember, that means we need to get y by itself using whatever operations we might actually have. So in this case, to solve this for y, I'm going to have to add 4 to both sides, giving me x plus 4 is equal to 1/2 y. And then to get rid of the 1/2, I need to multiply both sides by 2. So that gives me y equals 2x plus 8. Depending on how things are worded or what the problem is doing, this is your answer. That gave us an inverse, but we can also write it in our inverse notation instead. So our optional step here, unless they specifically ask us, is to write it as an inverse function. So here our original was f of x, so this is going to be f inverse of x equals our 2x plus 8. So those were kind of our distinct steps for finding an inverse. The last thing that we kind of did was we talked about how do we know if two things are inverses. So here we'll start with two functions. F of x equals 2x minus 1 and g of x equals, let's do 1/2 x plus 2. So for us to check if these are inverses, we need to do two things. We have to actually do the composition both directions. So we need to find f of g of x and see if that equals x. And if it does, then we need to check g of f of x. Both of these have to be true for it to be an inverse. If one of them fails, we can just stop, but we should go all the way through if it's going to work and we're going to prove it. So let's start with f of g of x. So that's saying that I'm going to take my f equation, which is 2x, and instead of x, I'm going to write the g equation. So g is 1/2 x plus 2, and then I have minus 1. I distribute this. This gives me x plus 4 minus 1, which is x plus 3, and that failed. It is not an inverse. We did not end up back at just x. For it to be an inverse, it must go both ways and end up back to the x. So let's say pretend that it did work out. Our next step would be to check the other way. So I take my g and I'm going to put the f of x in it. So my g of x equation is 1/2. And instead of x, I write the f of x, 2x minus 1. I distribute, so that gives me x minus 1/2 plus 2 is x plus 3/2. And again, we did not end up at just x, so no, these are not inverses. All right, so this was a real fast kind of whirlwind review of some of the key points. I will say the part that has probably confused the most people is looking at equations and asking what is domain and what is the range. And there's a couple things that you can do to try to make that a little bit easier. So the first is if they just give us some kind of weird equation and they ask you what is the domain and what is the range, this is kind of where people get stuck. And the easiest way is to picture what does the graph look like. So graph it on your graphic calculator, plot some points, but we just need enough to kind of know what the graph is doing. In this case, y equals 3x plus 2 has a y-intercept of 2. It's been moved up 2, and it has a slope of 3. So it looks something like this. Once we have some kind of ballpark as to what the graph looks like, it gets much easier to tell domain and range. So here, this is a line. It's going to go left forever. It's going to go right forever. So that means my domain is negative infinity to infinity. It goes forever to the left. It goes forever to the right. It goes up forever. It goes down forever. So my range is also negative infinity to positive infinity. When we tried to find intercepts, we had a specific method where we could try to find the intercepts if we can't just look at the graph and see. So for my x-intercept, we would say that y equals 0, and we could solve the equation. So that gives me 0 equals 3x plus 2. And if I solve this down, I get x equals negative 2/3. So there's my x-intercept. If I wanted to find the y-intercept, I could say that x equals 0. So that gives me y equals 3 times 0 plus 2, or just y equals 2. And that's a quick way we can find intercepts if we can't remember any other methods. All right, so I'm going to post a practice test. The practice test is the big key. So when I go to write the tests are very, very similar to the practice tests. It's oftentimes nothing more than I change the numbers or change the order around a bit. So make sure that you do the practice test and that you ask questions if you get stuck on it. If you have any questions, come to office hours. I open up the Zoom call every day between 11 and 11:05, and then again between about 3:50 to about 4:05. I open up the calls for that time period. So call in, get help as you need it.